Oh, yes, 4 weeks, and then you never have to do OCHEM again until you prepare for an entrance exam that might have it.
Unless you're taking your MCAT after this class.
And you know, I do build this course to help students do well on the MCAT or the DAT. I think pharmacy schools stopped requiring the P. I think they called it the PCAT. I'll be honest, I don't really teach this class for chemistry majors. When I was a TA at CU Boulder, they actually had a separate organic chemistry course for chemistry majors. And it was just more rigorous, more mechanisms, more reactions, more conceptual understanding. I try to, I think you guys can see this. Did I not give you one?
That's okay.
I try to give you guys both a wide view of all of the concepts that we're learning and a deeper understanding of what we're doing. So you're not just memorizing, but you have to understand it, right? And that's because when you leave, I want you to have those tools of being able to understand it. I don't want you to leave and be like, I remember that and I just forgot it and I'll memorize it again and still not understand it. You'll leave and say, I remember that and I'll relearn it. And because I have skills of trying to understand it, it will connect even better the second time. It's not just memorizing more strongly, it's understanding more strongly. That's my goal. My other goal is that you leave and get to see the organic chemistry in the world around you. Oh, it's all over the place. Sometimes I try not to think about it because it's so prevalent.
Do you want to know what I said today, Mom? I said organic chemistry has ruined my life. Because somebody texted me today and they were like, hi, I'm Noah. And I was like, NaOH. NaOH.
That's not how you spell Noah, by the way, but...
They spelled it like that. NaOH?
Now?
It was like NaOH. It's NOH.
N-O...
No, that's how he spelled it.
That's a weird way to spell Noah. But
I swear.
to each their own.
We also are in Utah.
Good point.
True.
Good point.
It's like Everly is Everleigh. Yeah, exactly. Riddle me that, okay?
All right. We've been talking about carbonyls quite a bit this semester. The whole second half of the semester is on carbonyls. And we probably could have had this discussion earlier, but it becomes a lot more relevant in this unit. So a little anatomy of the carbonyl. I'll be honest, I don't know what anatomy even means. Like, what is the linguistics behind it? So I might be using that wrong, but some terminology that I want you guys to be familiar with. The carbonyl carbon doesn't have a name, so we just call it the carbonyl carbon. But it is a central point in the reactivity that is possible around this functional group. Carbonyl is not a functional group, around this bond type. So relative to the carbonyl carbon, the first carbon off of it is called the alpha carbon. You guys might remember that in OCHEM 1 we said the alpha carbon was like the carbon of interest. Yeah? Like that's the one that has a functional group on it, or that's the one that has reactivity that we can do. Alpha cleavage even in mass spectrometry. But I want to point out the alpha carbon of the carbonyl is not the carbonyl carbon. So there's still interesting things that will happen, but this is just the first carbon off of that. The name for the second carbon off of the carbonyl carbon? Beta carbon. And we can go on. It's not very often that we have anything past beta. But do you guys know what comes after beta in the Greek alphabet? That is the phonetic alphabet. Gamma. Gamma comes after beta. Not Charlie. That's not the Greek alphabet. So these are the most important things for us, the alpha carbon, the beta carbon. And we've got some new functional groups that are going to kind of integrate some of this terminology. So some of the new groups that I want you guys to be familiar with. Can you believe we're in Unit 5 of OChem 2, and we're still learning new functional groups? Oh my God, I don't even teach you half the functional groups there are in the world. I just learned about these peptide coupling reagents. And like, if you were to give a name to that functional group, anyways, you just have to believe me.
I saw somebody say that the reason why there's so many different like reactions and functional groups and things you have to learn is because chemists can't admit they're wrong, so they just keep like making up rules. They're like, oh, actually, we just proved this, so it works, except in the case of half of the functional groups.
Amen to that. All right. I mean, I'm curious if you guys have any inclination about what we can call these. What might you call this functional group? Take into its entirety the carbonyl and the alkene. And recognize that the carbonyl is not a specific carbonyl. That could be an aldehyde, it could be a ketone, it could be an ester. And those are the three main functional groups we'll use in this unit: aldehyde, ketone, and ester. It could be H, it could be carbon, it could be OR, could be OH. We will have a little bit of carboxylic acids, so it could be OH. What would you call this? A carbonene. Okay. Yeah. This is the last unit in OChem 2. A carbonene, because that kind of takes generically carbonyl and combines it with an alkene. Although in terms of like suffix, it's usually the ene that comes before whatever carbonyl thing would come. So like could be an enone or an enal or an enoate, but that's not generic enough, and there's not a generic name for just the carbonyl. So to make this broader, this is often referred to as the alpha beta unsaturated carbonyl. I agree. Why are we calling it that? Alpha beta unsaturated carbonyl, because right. Because of the degree of unsaturation between alpha and beta. Is it a fair name? Alpha and beta are unsaturated. Should we review what it means to be unsaturated? Go ahead.
No, I was going to say, I thought it was the opposite. I thought saturation was
Pi bonds?
yeah.
Well, saturation means having the most possible. Wouldn't you agree that I could have more atoms bonded at alpha and beta? Instead, I have alpha and beta bonded to each other, rather than maximizing the groups that they can be bonded to. Saturation is bonding to the most groups possible. This is unsaturated. There's another name for this functional group. You will hear me refer to it as both. You're welcome to refer to it as either one. A conjugated carbonyl. Why would they call it that? What is conjugation? Next to? Keep going. What do you think of when you think of conjugation? It's important that you know what you think you know. sp2. How about like eat, ate, eats, ran, run? Are those conjugates? Is that conjugated? I've conjugated my verbs, right? How about a conjugate acid and a conjugate base? Why do we use that word conjugated for all these different scenarios?
Hydrogen?
What about
I
hydrogens?
don't know. How many are there?
Ah,
I don't know.
no, I'm not sure that the number of hydrogens means anything with conjugation. When we say that a verb is conjugated, we're saying here's one form of it, here's another form of it. It's the same thing, but it's different. When we say, do you disagree, James? When we say that we have conjugate acid and conjugate base, we're saying here it is before it has a proton, here it is after it has a proton. Here it is before it's given away its proton, here it is after it's given away its proton. It's the same thing, but different. And when we say that these molecules are conjugated, we mean that their pi systems are connected, that they're related to each other. They're actually the same, but they look different. So it requires sp2 or sp hybridized atoms. It requires p orbitals. There's a p orbital overlap giving this pi bond between the carbonyl carbon and the oxygen. And there's a p orbital overlap giving this pi bond between alpha and beta. Okay, well, if there are p orbitals here, 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 and here, what is stopping this overlap? Why would these orbitals, these p orbitals, not be overlapped? And if those are overlapped, that's a pi bond. So we're saying that these are related to each other. They are connected. They're in resonance. A conjugated carbonyl has resonance amongst itself. If we take a step back and we think about MO theory, we're actually saying that there are 4 atoms in this series. So there are 4 molecular orbitals in this conjugated system. The lowest energy is the one where they are all overlapped and sharing a set of pi electrons. The second lowest energy is where there is a node down the middle. And doesn't that look like the bonding character we actually see? It looks like the first 2 atoms in a pi bond. It looks like the second 2 atoms in a pi bond. It looks like individualized pi bonds. But it's actually the same 2 electrons making that individual pi bond behavior. And it's the other 2 pi electrons that are shared totally across all of them. So that is to say, there's a resonance form here. Which way can I expect electrons to flow in this conjugated system? Electrons always flow toward the more electronegative atom. So in this case, electrons will flow towards oxygen from the CO pi bond, which means they'll flow away from beta in the alpha beta unsaturated pi bond. And so I have a resonance form here that creates this electrophilic position on beta and a nucleophilic position on alpha. I feel like I should have done a different color. Okay. That's one functional group. Here's a new one. What would you call this? A what? An ether? An ester. No, it doesn't have to be. These could actually both be esters.
You just call it a hydride?
It's actually not, it's not a hydride. Are you thinking of the acid anhydride?
Yeah.
Where they share an oxygen?
Yeah, they're missing an oxygen.
It's missing the oxygen. So it's not an anhydride. It looks similar because it's got 2 carbonyls linked, But not being linked by an oxygen makes a big difference. What could you call it? Double ketone. Can we describe the relationship of the two ketones? How are they positioned relative to each other along their chain? You say geminal?
Yeah.
Actually, I think the only geminal ketone is the one you're exhaling currently. That's a geminal diketone. A symmetric diketone. But does that describe how many carbons are in between them that are symmetric to each other? So why don't we call one of these the reference carbonyl? What is the other carbonyl positioned relative to that reference? Beta. So we'll call this a beta carbonyl carbonyl. I know, that's a really terrible name. So I want to give you guys some example molecules that are beta carbonyl carbonyls. Here is a beta keto ester. Do you guys remember this compound? We named it back in the day. Do you notice how I've modified the terms carbonyl and carbonyl to specifically describe what types of carbonyls I have here? I'm referencing my ester as the primary carbonyl and saying that it has a ketone beta to it. Why didn't I call this a beta ester ketone? Why do I prioritize the ester over the ketone? Yeah, the ester is a higher priority functional group. So the ketone comes secondary to the ester. Okay, you know how to name this. Go ahead. Give its IUPAC name. We're going to deal with this a lot in this unit. I mean, like a lot, a good amount, enough. Sometimes. We'll see it. Andy's taken all of those words. What's the root? What's the suffix? What's the suffix stopper? What is going to show up in the prefix? Do you know you're going to do nomenclature on the final in 4 weeks? So this is a good time to practice.
I don't need to think about how soon it is.
Yep. We have to use the stopper for ester. Exactly. 08 is the suffix. Yep. Good. Ethyl, 3-oxo, butan, because the suffix doesn't have an alkene or an alkyne, so the suffix comes from alkane, and the suffix stopper comes from the ester. All right, that is its IUPAC name, and if you search it, you'll find it. But most people won't refer to it as that. Remember the name for the 2-carbon carbonyl? That acete prefix? This is an acetate ester substituted by an aceto group. So this is called ethyl acetoacetate. Again, describing the fact that there's a 2-carbon substituent off of my 2-carbon carbonyl. It's not just ethyl acetate, it's an acetosubstituted acetate, ethyl acetoacetate. Ethyl acetoacetate is what type of functional group? A beta keto ester, right? That's the functionality it has. And because of that, it has unique reactivity that we're going to leverage. All right, another functional group for us in this same vein is the beta ester ester. Just a subset of the beta carbonyl carbonyl, right? Most of the time I hear all of these referred to as beta keto carbonyls, but technically they're not always ketone groups. Can you see how this is a beta ester ester? Relative to one of the ester's carbons, the other ester carbon is beta to it. This is referred to as a malonic ester. And this one specifically has methyl chains, so this is called the methyl malonic ester. I don't know why I put it in parentheses. I was going to call it methyl malonate, but as soon as I started saying it, then it sounded wrong. No, but yeah, they call it that. Anyways, we're going to call it the malonic ester. It comes from the malonic acid, where both of those carbonyls are acids, so they call it the malonic ester. There can be all sorts of combinations. I'm pointing out these 2 molecules in specific because we're going to use these 2 molecules specifically quite a bit. Does that seem fair? But there can be beta aldehyde ketones. There can be beta keto ketones. There can be beta aldehyde esters. You guys agree with that? Any combination of 2 carbonyls beta to each other all classifies as a beta carbonyl carbonyl. Good, 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 good. All right, let's move on to a third one. Those seem so far away. They can't possibly be related to each other. I will say this functional group is one that I did make up. And it's largely because it doesn't actually have specific characteristics to it, like its own reactivity. So it technically isn't a true functional group. But it is a good way of describing the product of one of the reactions we're going to learn in this unit. So it makes sense for me to kind of introduce it here because I want you to recognize this bonding pattern. What relationship do those carbonyls have to each other?
Is there a beta carbon in the middle?
Yeah. Is that what you said?
Yeah. That's what I wrote, yeah.
Can I see it? Yeah, that's what I call it. I call this the shared beta dicarbonyl. Great job, Andy. There's a reaction that we'll learn called the Michael addition. Love that. Good for Michael. And the Michael addition yields a shared beta dicarbonyl. So by being able to recognize that those two carbonyls have alpha carbons that are both bonded to the same beta carbon, you can make sure that you're drawing your product correctly. And the shared beta dicarbonyl, depending on what the R groups are, can sometimes go through intramolecular reactions. We're going to learn about that type of intramolecular reaction as well. All right. I believe those are... actually, I know this kind of sucks. Can I go back down and give you another version of a beta carbonyl? This isn't a molecule that we're going to use so much, but it's a format that I do want you guys to recognize because we'll use this format. So I'm going to leave this one generic and call it a beta carbonyl acid, which means the other carbonyl could be an acid, an ester, a ketone, an aldehyde. But that really just means that I've got a carboxylic acid on one side and an ester on the other. And what's beautiful about this functional group is the way that it reacts within itself. When we provide heat to this system, it arranges into this high energy transition state. Well, it's not super high energy. Well, that's not actually a transition state, sorry. It arranges into this high energy conformation, this six-membered ring essentially, but you can see how it's not actually a six-membered ring. It's not connected. And this is why the R group doesn't matter. So this could be a beta keto acid, a beta ester acid, a beta aldehyde acid, a beta acid acid. Doesn't matter what's going on with this R group. What matters is that given the beta position of the one carbonyl, the acid can arrange itself into this six-membered transition state. And that's going to allow us to do a very fun reaction. I'm going to tease you with it and not tell you what it is. Okay. All right. So an important part of the chemistry of the carbonyl is the alpha hydrogens. These alpha hydrogens, sorry, I'm looking for a word, but I can't think of it. They're like more acidic than normal CH bonds. I don't want to say especially acidic, like they're not super strong acids, but they're comparatively acidic. They dabble in acidity. They are relatively acidic. Surprisingly acidic. Ah, that's a good one. So we're going to take advantage of some of their acidity. But first, I want you to go through on the top of this worksheet and simply identify alpha hydrogens. Deal? See where you can find the alpha hydrogens. See if you can count how many alpha hydrogens there are. Hmm? Hmm? Mm-hmm.
So for this one, would these both be an alpha carbon?
Mm-hmm. Good. Alpha in both directions. Is this you circling the alpha hydrogen?
Yes.
Where's the alpha carbon?
Here.
Oh, I don't think so.
Wait, is it just
That
one
in
of them, or if it's like, can there be multiple?
Yeah.
Oh, okay.
So this carbon here is the carbonyl carbon.
Oh.
The alpha carbon will be bonded to the carbonyl.
Okay.
There you go. So what is this? Just an aldehyde hydrogen.
So
But
it's not alpha.
it's not an alpha
They're
hydrogen.
just
To be an alpha hydrogen, it will need to be bonded to the alpha carbon.
okay.
She did. She said that in front of everybody.
And then Ella said, I agree. So.
Who did this?
I said I agree.
Yeah.
I don't remember this.
Are you saying how many alpha hydrogens there are?
3. Oh, am I supposed to say how many?
I don't know. How many are here? How many alpha hydrogens?
Well, there would be 3 on this one because it's a CH3. So there would be 4 on this whole molecule.
How many on this? 4
Um,
alpha hydrogens on the whole molecule?
Wait, I thought
Yeah.
there's not an alpha. Because does
If
it
it's
has
not
be
bonded to the
attached
alpha carbon,
to an alpha carbon.
yeah. Yeah. That's the deal.
have to be attached. Well, nobody ever said that.
That's a good point. Nobody ever said that.
Nobody told me that. I'm just.
But to be the alpha hydrogen, it is the hydrogen of the alpha carbon. Now you know. Now I said it. But you're right. I actually think that's what I meant to say instead of surprisingly acidic anyways. Identify the alpha hydrogens connected to the alpha carbons. But they are surprisingly acidic.
I'm so tired. Literally everyone is so I'm like, dude, why are you here?
Looks good. Doing good. You highlighted this in blue just to say that it's an alpha carbon.
Yeah.
Good.
And then I wrote my actual hydrogens.
Good. How you doing?
That's all of them.
I see him now. Yep. Great work. Yeah. Mm-hmm.
Oh, yeah, you're right.
True or false? Every carbonyl has an alpha carbon. Can you prove it?
What's when it's like number 2?
Say that again. Formaldehyde. I thought you called it carbaldehyde, which might be correct. Formaldehyde's a great example. No alpha carbons, no alpha hydrogens. What else? Jackie, did you say one?
Same thing.
Same thing.
Couldn't figure out the name of it.
A nitrile. You know what? I'm not as familiar with them referring to nitriles with alpha hydrogens. They might. I'm not sure that they do. But we won't explore it, unfortunately. So that's not a bad idea because it technically has the same amount of conjugation. Yeah. What other? CO2. Okay, I don't know if I'll put that one up here either. Maybe. Yeah, CO2 is it's interesting. You can argue that CO2 is not organic because it has no hydrogens in it, that it's inorganic for not being a hydrocarbon or derivative. But then again, they call methane tetrol, so that's COH, OH, OH, OH. They call that an organic molecule, and that has no hydrogen to the carbon. It's a gray area. Yeah, okay, CO2 has no alpha carbons. Anything else? Actually, all of our form groups, like formic acid, methyl formate, even dimethyl formamide, have no alpha carbons. Okay, so we've established that not everything needs to have an alpha carbon. What is the maximum number of alpha carbons that a carbonyl can have? The maximum number of alpha carbons that a carbonyl can have, 2. If I try to add a third bond here, ooh. I see what you mean. The maximum number of alpha carbons, 2. Esters and aldehydes, the maximum number that they can have is 1. Doesn't matter what else is connected to that alpha carbon, that is the most alpha carbons an ester or an aldehyde can have. A ketone can have 2 max, and that, again, is what makes it a ketone, is that it has 2 carbons on either side. All right, so what's the maximum number of alpha hydrogens that a carbonyl could have? That would be on one side, yeah? So 6. So acetone actually has the most alpha hydrogens out of any compound in existence. Congrats to acetone. It's unique for once. Sorry. Its name is also unique. I'll tell you I hate its name, acetone. It is more than 2 carbons. It's just 2 carbons in both directions. I literally, no, I'll stop. What's the least number of alpha hydrogens that I can have? 0. For instance, not having any alpha carbons, or not for lack of having alpha carbons. Here is ditert-butyl ketone, 0 alpha hydrogens. So we can have this whole spectrum, right? We can have all the way from 0 alpha carbons up to 2 alpha carbons. We can have 0 alpha hydrogens with 2 alpha carbons, 6 alpha hydrogens with alpha carbons. Big spectrum. All right. Now let's talk about why these alpha hydrogens are surprisingly acidic. I first want to give you some reference. We've learned the pKa of some other acids over OChem 1 and OChem 2. The pKa of an sp3 CH bond. I'm going to organize this a little bit. No, I guess I won't. The pKa of a normal CH bond is in the 50s to 60s. How good is that as an acid? That's actually about the strongest base we have. The pKa of hydrogen is in the 40s. Molecular hydrogen is a better acid than an sp3CH. An sp2CH is in the 40s somewhere. An sp3NH is in the 30s. An sp-CH is about 25. Okay, so that's the range that we've looked at in the past for some things. This is why we have to be careful when we're dealing with organometallics, because we're dealing with the conjugate base of a very bad acid, which means we're dealing with a very aggressive conjugate base. One of the reasons that we use sodium hydride and sodium amide when we need to do things like the Williamson ether synthesis, or to deprotonate an alkyne, or to do elimination and form an alkyne, is because these are super good bases without being super aggressive. This is where our alpha carbons are going to fit in. They're going to fit in all beneath our SPCH. We're going to look at a few different characteristics. I think actually I want to give you guys some more perspective. We're going to look more here. The acidity of an alcohol is in the teens. We say that this is roughly 15 to 18 pKa. The pKa of phenol is about 10. That depends on if it has electron withdrawing groups that can actually contribute in resonance. And the pKa of a carboxylic acid is about 5. I think I'll add one more for you, just for context. The pKa of protonated water, which is very similar to the pKa of a protonated alcohol. That's got an acidity, a pKa value of about -3. So if you have hydronium, you have a better acid than a carboxylic acid. Carboxylic acids are protonated in acidic conditions, but carboxylic acids are named acids by all the rest of functional groups for a good reason. They're quite acidic. All right, we're going to pay attention to the alpha carbons, the alpha hydrogen acidity of 3 functional groups, the aldehyde, the ketone, and the ester. We're not going to pay attention to the alpha hydrogen acidity of a carboxylic acid because it is not the most acidic hydrogen in the system. The carboxylic acid is the most acidic in the system, so we're not going to consider it. Does that make sense? It's not going to get deprotonated anyways. So factors that impact our alpha hydrogen acidity. The first is induction, but really we can just consider the functional group. We can rank the acidity of our alpha carbons based on the functional group. Okay, here's my alpha CH of an aldehyde. The alpha CH of a ketone, and the alpha CH of an ester. The reason that we're saying induction plays a role here is because the less induction I have, the better, the more acidic that alpha hydrogen is. This hydrogen does not have a lot of electron density. What it does have, it pushes towards the carbonyl, which is pushing up against the alpha carbon, which makes it harder for that alpha carbon to hold a negative charge. The hydrogen is pushing negative charge in its direction. It makes it hard for it to be an acid and hold a negative charge. But a hydrogen does not have a lot of electron density. An entire carbon group has much more electron density. So when you have a ketone, this carbon group is pushing more and more electron density, making it less likely that that alpha carbon actually acts as an acid.
We're assuming R in that case has to be carbon.
Yeah, we're saying aldehyde ketone ester. Good question. Now, when I have an ester, I think you guys will agree, esters actually have the reverse inductive effect from that carbon, right? Shouldn't that have the opposite effect? If I'm not pushing electron density in that direction, which makes it harder to be an acid, but I'm pulling it, why is this the least acidic? That's the problem. Why is it less likely to donate a proton if electron density is being pulled towards that O? It's because this O is in resonance with the carbonyl, which effectively is a huge push of electron density. You guys know how I say that everything is magnets, right? Right now, we're trying to consider how well can this carbon be a magnet with its hydrogen? How well can carbon attract something to take its hydrogen away and leave carbon with a negative charge? We're saying here it does so all right, but it's got some more negative charge coming its way. Here it's got even more negative charge coming its way, so it's not going to be able to take this negative charge very well at all. Here we're saying the oxygen should be taking charge its way, but because it's in resonance, it is effectively swinging all of that electron density around this alpha carbon, near this alpha carbon, makes it harder for that alpha carbon to hold on to a negative charge. All right, so we're saying that this is most acidic, greater than, least acidic. And after they act as acids, sorry, I didn't give the numbers here. I always forget these numbers, to be honest. We could see if I can wing them, but I think I have a way of pulling them up. Tells you how important it is to know exact numbers, doesn't it? I'll come back to the numbers. Can you draw the resonance form? Sorry, can you draw the conjugate base for each of these structures? This is not going well. I have not finished the rest of my structures, so it might be best for us to just say that these are methyl groups as alpha carbons. Oh, did I draw CH3? That makes no sense. So here's a conjugate base. Can you draw the conjugate base for the ketone and the ester as well? Why would Chrome not be letting me into OneDrive? That's very weird. Okay, this I was not expecting. We might have to guesstimate these numbers. Oh, I could just look up last semester's video. Is that cheating?
You're using your resources.
Wow, what a good way of saying it. Thank you. Honestly, who taught you how to say that? All right, now, we could have drawn a similar conjugate base for all of those other things, all of those other groups that we had listed before. Why, oh why, are these alpha hydrogens more acidic? I'm not giving you a number to show you how acidic they are, but they're somewhere between the teens and the 20s. Why are they more acidic? If I'm still placing a negative charge on the carbon, why is that more acidic? Any idea? It's resonance. Can you draw the other resonance forms of these conjugate bases? Okay, I got my numbers. The pKa of the aldehyde is 17. The pKa of the ketone is about 20. The pKa of the ester is about 25. Those are orders of magnitude different. In resonance, there is no C minus. Which of those is a major resonance form? Why? Exactly. It places charge appropriately. So because there is a better resonance form, that carbon is surprisingly acidic. The oxygen helps hold on to the negative charge. In the conjugate base of the ketone and its resonance form, again, the only distinction here is that it's got more electron density butting up against that newly formed negative, making that negative more likely to act as a base, less likely to ever form. The ester technically has 3 resonance forms that we can draw. There's the CH2 minus, where the carbon has acted as an acid. There's the resonance form with O minus. But there's also this resonance form that kind of highlights why carbon is not allowed to be such a good base. And that's the idea of the ester oxygen donating into the carbonyl, pushing more electron density out towards that alpha carbon anyways, making that alpha carbon less and less acidic. Okay, so if I were to give you a molecule that had both an ester and an aldehyde, both of them have only one alpha hydrogen, which is more acidic? Where will a base be more likely to deprotonate? At the aldehyde's alpha position. Simply due to the functional group. And that functional group is affecting the induction. By the way, this conjugate base that we formed, these are called enolates. You can kind of see how they are alkenes and the conjugate base of an alcohol. So it's not an enol. But it's its conjugate base, the enolate. Do you guys remember learning about the enol? I want to say you should have learned it from OChem 1. But again, it's just a combination of alkene with alcohol, the enol. This is the conjugate base of an enol is an enolate. There's also the conjugate base of the carbonyl. Is it strange that carbonyls and enols share a conjugate base? It might be, but we'll explain why in a minute. Okay, we've got two other factors. Do you guys want to take a break? Yeah. Let's take 7 minutes. Get up and move around and get your blood flowing. And then why don't you come back in here and we will talk about those two other factors and then talk about what relates the enol and the carbonyls through the enolate. It's okay.
Can you talk about why the aldehyde is more acidic than the ketone? Because it doesn't, like, I don't think, I feel like with ketone, there's more hydrogen density. Therefore, it should be more likely to just, like, on the other side, be willing to give one out. Because there's just, like, more hydrogen hanging out. Like, that's where my mind goes. I don't really feel like, and it makes sense for the, you know, the alcohol or whatever, the ester, but like there's another oxygen, so just like from electronegativity, that alpha carbon is not going to be as willing to like give off the hydrogen. But I feel like, yeah, that doesn't really work when we see the actual rankings.
I hear what you're saying, that more hydrogens, more chances to be an acid. Statistically, shouldn't it be more acidic? But the electronics don't really care about the statistics. The electronics are saying that this ketone has a bunch of electron density that is being pulled towards the carbonyl by the electronegativity of the oxygen.
Right.
And because of that, the cloud of electronegativity, or the cloud of electron density, is butting up over here as well, making it more partial negative than you might expect it to be, making it harder to be an acid. We want a stronger partial positive, more so than a partial negative.
Yeah.
I think the other way that you could think about it, although this is sometimes dangerous, is sterics, which is to say that, again, this takes up some space that makes it hard for something negatively charged to get in here.
Yeah. Okay.
I actually would say that the ester is the one that seems confusing from the induction perspective, because the oxygen is pulling electron density towards itself. You should think that that creates a larger partial positive, which means that it could hold a negative charge well, because oxygen is going to take some of that. But because of oxygen's ability to engage in resonance, it counteracts any of the inductive effect that it also had. If you remember when we discussed ranking carbonyl groups by their electrophilicity, we said the ketone was less reactive than the carboxylic acid. And we said the ketone has inductive effect pushing towards the carbonyl. That shrinks the partial positive of the carbonyl. But the oxygen of the carboxylic acid should have inductive effect away from the carbonyl. That should grow the partial positive on the carbonyl carbon. But because of its resonance with the carbonyl, it more than accounts for any inductive effect out. Similar here. Because of its resonance, it kind of counteracts any inductive you think would be helpful. I know it kind of is confusing. The nice thing is you can just easily rank aldehyde, ketone, ester.
Yeah, I think your idea of like if bound with negative helps explain that more.
Good.
Makes a little more sense.
A little bit. I wish you guys could see the things in my head. And then other times, no, you're lucky. You don't need to see this. But I do wish I had someone that could animate things for me. Like my perspective on molecules. You guys ever seen like animations of cells? Yeah. And you can see like things floating around and like moving towards things. That's okay, but it actually, it's like filming something underwater. You can see the fish floating and the corals swaying, but you're ignoring all of the fluid that everything is suspended in. And that's true in those animations of cells as well. You're just ignoring all of the fluid. The fluid is molecules, and those molecules are important because they're being produced by chemical reactions or consumed by chemical reactions. I think about that too when they show animations or even like pictures of neurons in the brain. And it looks like this big empty space between these neurons, and they're just like reaching out to grab onto one another. It's not vacuum in your brain. Like it's not.
It sounds to me like you want to be a biochem professor.
What am I saying that's giving you that impression?
What?
Can you do that, please? I still need to take it. I need to take it too.
This is an attack.
It's loving.
First of all,
Thoughtful.
we don't teach biochem at Slick.
Where?
We have bioorganic chemistry 1120, which is an overview of OChem 1, OChem 2, and biochem in one semester.
That sounds horrible.
So instead of doing all of
Why
this,
is it 1120?
it's a nursing major's chemistry. Elementary bioorganic chemistry. Instead of doing all this stuff, instead of like learning oxidizing and reducing reagents, you just write over the arrow O, and you just say like alcohol gets oxidized to carboxylic acid. And then to say it gets reduced, you just put H in brackets. I had a student that was taking my OChem 2, I think my first OChem 2 semester, while she was taking that course. She wanted that course so that it could like help give framework for doing well in OChem 2. She didn't need. And she was like, I think this course is helping explain things in that course that I'm not understanding, more so than that course explaining things in this one. Because when you skim over stuff, like you can't make sense of it. You don't have the time to. You just have to accept the change for what it is and move on.
Doesn't that cost like 6 credits?
Not here. No, I think it's 4.
I think at the U, I swear my friends say 6 credits there.
Was it maybe combined with the lab?
Maybe.
Unentangled? Because then I could see it being like 5 credit lecture and a 1 credit lab.
Is it before the nursing program? Yeah.
Yeah, it's a prereq.
I would have taken it and it was not. Did you take it at the U? No, I took it here. I was like getting ready to apply for the nursing program and then I had all my prerequisites done. And I was working as a CNA and I was like, I fucking hate this. Yeah. I was like, I have to see another bubble.
I'm not sure what I just heard. All right, let's move on to our next factor. We've got 3 factors. So actually, can we take a step back? Why is it that the alpha carbon is so much more acidic than other sp3CH carbons? Yeah, the sp3CH has an acidity of 50 to 60. And we're saying even the worst alpha carbon, the ester, is 10 to the 25 times more acidic. By the way, that's like saying for every mole of acid that, for every mole of alpha carbon that gets deprotonated, there is one other sp3CH that gets deprotonated. That is crazy big numbers. Why? What is it that makes the alpha carbon so much more acidic than other CHs? It's by the oxygen, but that's part of it. It's in resonance with an oxygen. The resonance with the oxygen greatly changes the acidity here. Okay, now the substitution of an alpha carbon also changes its acidity. So let's compare our aldehyde as it moves from a primary carbon, a primary alpha carbon, to a secondary alpha carbon, to a tertiary alpha carbon. How do you suspect acidity will change? Does it get more acidic or does it get less acidic? Yeah? Anything to base it on?
Basically, oh wait, no, it gets less acidic.
You're thinking similar to how the ketone gets less acidic because there's more density, this should be less acidic. All right, well, let's draw out the conjugate base. But let's draw the conjugate base in its most stable resonance form. So although the alpha carbon gets deprotonated, the most stable resonance form will be the enolate. So let's draw the enolate form for all of these conjugate bases. Well, I started off pretty poorly because I did not draw an enolate, I drew a carbonyl. I also did not leave space for me to put the pKa's. I'm doing great. Any issues with these enolates? Do you agree with these enolates? Do you understand how I'm going from that condensed structure up above to the bond line below? The methyl groups are all staying in place. Which of these looks the most stable? What's different about them? More substituted alkene. So Katie, you said the one on the right looks like the most stable. It's the most substituted alkene. Do you have any feelings about substituted alkenes?
Well, I mean, that one is the most substituted, so it'll have better resonance.
Better resonance, I'm not sure what better resonance is. Resonance is resonance. Oxygen holds the charge in all of them, so really the only difference is the alkene. And we learned in OChem 1 that a more substituted alkene is a more stable alkene, which means this is now the most acidic. So acidity trends against induction. The more induction there is, the less acidic. But acidity trends with substitution. So this is less acidic, less acidic. We already saw the pKa for the first one. That was the pKa around 17. Now we're looking at a pKa of 16 for my secondary alpha carbon and a pKa around 15 for my tertiary alpha carbon. What makes a bigger impact in acidity? The type of functional group the alpha carbon is attached to, or the degree of substitution the alpha carbon has? The functional group plays orders of magnitude difference, but the degree of substitution plays about an order. I mean, that's not a small feat, right? That's 10 times more acidic. But that's compared to the aldehyde being 1,000 times more acidic than a ketone. And the math here is always hard for me. 10 million times more acidic. No, 100 million times more acidic than an ester. So the functional group plays a huge role. 100 million times more acidic, just 100 times more acidic. All right. So let's see if we can apply this as well. I'm going to draw this one up here. Which of these carbons is the most acidic? Which of these has the lowest pKa? The ones further away are the more acidic. Don't forget, it's being in resonance with the oxygen that really brought the acidity down from 50 down to the 10s. So there should be two places that you look in this molecule. Tell me what you're thinking. Which, right where? Here. Okay. Why not this? This is more substituted. That is not an alpha. So when considering resonance, beta has no resonance. Yeah? If there's no resonance, there's no stability. This has a pKa in the 50s. But these have pKa's in the high 10s. A primary is less acidic than a secondary. So most acidic. Notice I'm not saying least acidic, I'm just saying less acidic. The least acidic would actually be that tertiary CH. All right. Last thing. This is the amount of resonance. All of these conjugate bases have had the same amount of resonance. They've all had two resonance forms. One major resonance form where the negative charge is on the oxygen. What if I could increase that resonance? How would I do that? get an alpha carbon that is shared by 2 carbonyls. So that structure on the left we've got pKa's between 17 and 20. But what about this CH in the middle? How many resonance forms can you draw for it? Two major or 2 total? Here's the first one we should think of drawing because it's the one that forms when carbon loses the hydrogen, but it's not a major form. I've got a resonance form where the oxygen on the left holds the negative charge, and I've got a resonance form when the oxygen on the right holds a negative charge. Do you know what? I made a small mistake here. I drew a beta keto ketone. I meant to draw my beta keto ester, like acetoacetate. So that meant to be OR. Because again, those are the ones that we're going to use a lot. So they're relevant here. Okay, there's another one. We've got our malonic ester as well. And again, the malonic ester has these 2 major resonance forms. Negative charge held by the left-hand oxygen, negative charge held by the right-hand oxygen. Do you agree that the resonance is increased from all of the other alpha carbons? Not only is it increased, but the additional resonance form also puts a negative charge on the oxygen. So it's an increased major resonance form. Can you approximate the pKa's? First, can you approximate which pKa is higher or lower? Acetoacetate's pKa or malonic ester's pKa? Go ahead. I'm willing to listen. How can you reason which of those shared alpha hydrogens is more acidic? Everything you need is on the board still. They're not the same. They've got different pKa's. They share the same bonds. Which one? Here? Why is this more acidic? Because? They share the same amount of resonance. They both have the same number of major resonance forms. Yeah?
I think I'm confused as to what I'm looking at, to be honest.
Yeah, so
It's okay. I know.
here's a hydrogen that gets removed, so the electrons are held by the carbon.
So which one are we trying to decide is more?
Is this more acidic or is this?
Oh, okay.
Top right would have better reduction.
Yep. The combination of functional groups changes. I've got ester and ester versus ketone and ester, and we already know that esters have less acidic alpha hydrogens than ketones. So if both of them have an ester, that's not changing. But one has a ketone and one has an ester, that's the point of difference. All right, so this is our less acidic structure. This has a pKa around 13. That is 10 to the 12 times more acidic than just a normal ester. Yeah? It's even 100 times more acidic than an aldehyde. Although, like, that's a little surprising. The aldehyde is still that good at being an acid that an ester needs to have 2 resonance forms. So can you predict a pKa for this? Yeah, close, 11. More acidic, not by a lot, but more acidic, 100 times. Cool. So we will be doing some mechanisms that involve these resonance forms. A lot like what I told you guys in our aromatic substitution chapter, I will only be asking you to show the major resonance forms during a mechanism. And we will have mechanisms for this unit. So when you draw these mechanisms, you're allowed to draw any and all of them, but there are some that I want to see the major resonance forms. All right. Questions on ranking acidity? Ella.
Can I ask you a question about the substitution part?
Yep.
Going back.
Yep.
How did you say that? Because the one on the very far right, that's the most acidic. But if it's more stable, if it's more stable, then wouldn't it be less likely to act as?
Well, that's the point. Its conjugate base is more stable,
Oh, yeah.
which means it's less likely to reverse.
Okay.
Yep.
But how did you say though that like it's more acidic because it has like more?
A more stable conjugate base.
And it's more stable
Because it's a more substituted alkene.
okay.
So more stable conjugate base because it's a more stable alkene.
Okay. And it's because of the substitution.
That's right.
Okay, and you were pointing out on this long left that the single ester had 3 resonance forms, and the one two only had 2.
I just didn't show the minor form. This form is minor because carbon holds the negative charge, so I just didn't show it here.
So they have the same amount of resonance forms. The only difference is that induction P.
Correct.
Okay.
Same amount of resonance, only difference is induction, or the change in the functional group. Good.
Yeah, okay.
We can leverage this in our chemical reactions. First of all, these are more acidic than alcohols and water, which means that we can actually use sodium hydroxide or sodium methoxide or sodium ethoxide as bases. They are good bases to these because these are more acidic than them. These don't have the best acidity when compared to like sodium hydroxide and sodium methoxide. But we can still take advantage of some of their reactivity, and we'll be using acid-base chemistry to do reactions a lot in this unit. All right, I want to transition from acid-base chemistry into some of the things that acid-base chemistry can do for us. One of these things is tautomerization.
still don't like, are we just missing an OR? Like, what, I just don't even understand, like, what is on the board. I mean,
The OR on one side of the.
it's missing an OR?
Oh, here?
Yeah.
Yeah, I did forget
Okay,
that.
I thought those were like different structures, and I was like, I don't understand like what's going on.
Thanks for pointing that out. I forgot my ester group.
Okay.
Yeah.
And then on the, what's happening in the.
So this was just a comparison. Remember, the ketone has acidity 17 to 20 depending on its substitution. But this is not just a ketone or an ester. It's locked between a ketone and an ester. So its acidity is much lower, 1,000,000 times lower. That's what we're saying. A pKa of 17, not very acidic. A pKa of 11, that's getting closer to acidic.
Okay, and it's more acidic than the two esters because the esters have more of a role.
Yeah, we saw earlier that ketones in general are more acidic than esters.
Okay.
So by having this difference of swapping an ester for a ketone, this ruins the acidity relative to this.
So the oxygen is what makes it more acidic though, because that's like double or close to double the acidity of the ester group with normally.
Double. Actually, pKa is a logarithmic scale. So the ester normally was 10 to the 25, or sorry, pKa of 25. So here having a pKa of 13, that's not double the acidity. That is 10 to the 12 times more acidic, which is a trillion times more acidic. So for every trillion of these carbons that get deprotonated, one ester alpha hydrogen gets deprotonated, 1,000,000,000 to 1, 1,000,000,000 times more acidic. It's crazy.
Just because it has more resonance?
Okay. And not just more resonance, but more resonance on a negative, or with an oxygen holding the negative charge. For instance,
There's more resonance forms.
more resonance forms is a big part of it. If I have more resonance, it's going to be more stable.
Okay.
Putting that charge on an electronegative atom is another big part of it. If I had more resonance forms, but it just put more negative charges on carbons, it doesn't improve the acidity that much.
Okay.
But more resonance and putting that negative charge on more oxygens, win-win. Good.
Thanks.
So our last topic for today is tautomerization. Of course, tautomerization is just the changing between tautomers. That's obvious. But what is a tautomer? It's a name that doesn't really describe itself. Tautomers are chemically interchangeable structural isomers. That's a mouthful. Did you know that most structural isomers cannot be interchanged? For instance, propene and cyclopropane have the same chemical formula but are structural isomers. Ethanol and diethyl ether are structural isomers. No, dimethyl ether. I'm glad that you gave that skepticism. Ethanol and dimethyl ether are structural isomers. They cannot be chemically interchanged, at least not easily. That's the idea with tautomers, is that they're structural isomers, but they can be chemically converted. And there's two catalytic processes. There's a base catalyzed tautomerization. For instance, if I take, I'll start with this enol. If I start with an enol, and I introduce it to base, that enol tautomerizes into, specifically in this case, an aldehyde. Because I have a primary enol, I get this aldehyde. In fact, this is what happens during the hydroboration oxidation of alkenes. Hydroboration oxidation leaves me with this enol, but the base that is present catalyzes the tautomerization. And tautomerization goes both ways. So if I have an aldehyde in the presence of a base, I can tautomerize it into an enol, but equilibrium favors one over the other. D, according to my arrows, which way does equilibrium favor? Good. Carbonyls are always favored by equilibrium. At any time, there's more carbonyl than enol. Do you think you can propose a mechanism for this? What type of conditions are we in? Acidic or basic? We're in basic conditions. What's the base? Hydroxide. What's the acid? The enol. So my first step in most acidic or basic conditions is to do some acid or base chemistry. So my base deprotonates my enol, and it yields an enolate, which of course also water. An enolate is in resonance with its alpha carbon Which of these resonance forms is more stable? When the oxygen holds the negative charge, the enolate, or when the carbon holds the negative charge? Yeah, the enolate is more stable. Oxygen holding that negative charge is more stable. Which of these is more reactive? The carbon holding the negative charge. Because if it has that negative charge, it's going to do something with it. Like share it as an acid to become protonated. So, of course, the carbonyl form is higher concentration at equilibrium because that depends on the alpha carbon acting as the base. The enolate form depends on the oxygen acting as the base. So when we did hydroboration oxidation of alkenes, we made this enol in basic aqueous hydrogen peroxide, and the base catalyzes the tautomerization. Very cool. Can it be acid catalyzed? Of course. Acids catalyze so much. I mean, we had acid-catalyzed acetal formation, acid-catalyzed imine, oxime, hydrazone, enamine formation, acid-catalyzed esterification, acid-catalyzed hydrolysis, acid-catalyzed hydration. And we saw some of this in OChem 1 again. The tautomerization from an enol to a ketone in the oxymercuration reduction mechanism. Oh, I'm crazy for saying this. What? Sorry. Hydroboration oxidation of the alkyne, not the alkene, gives an aldehyde. And the oxymercuration of the alkyne gives the ketone. So these are even reactions that we've seen this semester as review. Acidic conditions or basic? Acidic conditions. So, which way do you want to see, by the way? This is a catalyzed equilibrium. You can go either direction. Should we catalyze the tautomerization to the enol, or should we catalyze the tautomerization? Yeah? We can do both. We can come back and actually do the backwards of this and the backwards of that. All right, I'm going to redraw my acid down here. I know my acid is H3O+, but what is my base? It is easy to think the OH is the base. We've been protonating the OH quite a lot. But we've been doing that in hopes of getting it to be a leaving group, right? But I don't want it to be a leaving group, would you agree? I actually want that oxygen bonded where it is, which means the alkene has to be a base. And alkenes are bases. We saw that in OChem 1. Alkenes act as bases in the presence of acid. And this isn't just a normal alkene. This is an enol. So when the alkene acts as a base, the oxygen is there to donate its electrons. My conjugate base is water. What did I miss? That's my next step. I missed something on my drawing, though. Just here. Nice. You all got it at the same time. That positive charge on oxygen. Water acts as a conjugate base, deprotonates it. Here I showed you guys some resonance. Did you know you didn't need to see resonance to do it? And I could have actually shown some resonance here as well, but it's weird because it puts two charges in the structure. Okay, let's do the reverses. Let's show the base catalyzed tautomerization of this aldehyde. Let's show the acid catalyzed tautomerization of this ketone. And if you want to, you're more than welcome to only show the major resonance form. By the way, if I were to redo this by only showing the major resonance form, I would actually be able to show oxygen getting, I would be able to show the carbon getting protonated at the same time that the oxygen forms the double bond. I didn't have to show this second resonance form to show the carbon getting protonated. That all happens at once. It can happen at once because resonance forms are what? Imaginary. They don't exist. They're just simplifications for us. This is actually more like what the molecule looks like when it does this step. This is not what the molecule looks like when it does this step. Okay, see if you can draw those resonance structures or those mechanisms. You've got 4 minutes, go. Think about acidic conditions, think about basic conditions. What's your acid? What's your base? What's this? Acid or base?
It's base.
So what's this?
That's our acidic hydrogen.
There you go. So show the hydrogen. Yep. What?
Oh, she was just saying she's tired.
I طبعا. What's your acid? What's your base? What's this?
Not right.
Acid or base?
The base.
So where is your acid?
Not here.
Where? What's the acidic part?
But,
This was right. You didn't have to erase that. That's what I had.
the oxygen?
Yeah, does the oxygen have a hydrogen to give away as an acid?
No. So the carbonyl carbon.
Does the carbonyl carbon have an acidic hydrogen? It has a hydrogen. It has the aldehyde hydrogen. The base can do acyl addition, but that does not do tautomerization. Notice how there was no acyl addition here. Alpha hydrogens are surprisingly acidic. So if you're looking for an acid, you'll have to draw out the CH bond. She said, I don't care if I have to draw out the CH bond. I'll just point at the carbon and you can infer what I mean.
Okay, no, look, I did it.
You did it. Good. Now, think about the major resonance form. And if you can, just draw the major resonance form. All right, we got 1 minute left. Sorry. You guys want to see the answer, or should we just pick up here on Thursday? No, we're not going to talk about tautomerization much on Thursday. So if anything, it would just be a segue for us. Here's my base, here's my acid. The alpha carbon is the acid. I'm going to show the formation of the major resonance form. Did you say you got it, Peyton? Good. As I form my major resonance form, that is an enolate. I could have formed the other resonance form. Again, it really doesn't matter. Now I just protonate the oxygen. Whoops, and then I didn't actually protonate it. Okay, here's another issue that I'm kind of running into. I drew my enol trans instead of, or cis instead of trans, but these structures like being trans better, less steric strain. Okay, there's my base catalyzed tautomerization. Deprotonation of the alpha carbon, protonation of the oxygen. What's my acid here? H3O plus. What's my base? The oxygen is my base. So I'm going to protonate my carbonyl oxygen. Now what's my acid? What's my base? H2O has become my conjugate base, so the alpha carbon has become my acid. Once again, I forgot my positive charge. Two steps, that's it. So how come I never taught you that in OChem 1? I don't know, maybe I got lazy. All right, thank you guys for your time. We'll work on the back side reactions with these alpha carbons next week. Not next week. You know what I meant though, right? Yeah.